Hi, it's Rob. Welcome to another video in the Infrastructure as Code on AWS with Terraform playlist, where we'll provision a Lambda function with layers using Terraform. And the application that we'll be deploying will be a website screen scraper using Python, Selenium, and the Chrome driver. Please note, however, that even if the screen scraper app doesn't interest you, the process of packaging and deploying the resources in Terraform will be the same regardless of the app you're working with. Also, if you're new to Terraform and concepts like modules, locals, and outputs aren't familiar to you, I recommend starting with the videos at the beginning of this playlist to build a foundation before following along here, as I won't be taking a deep dive into all aspects of the Terraform implementation. Now, with that out of the way, let's get started. Now, before we jump in here, please note that all data on the official Tour de France website is owned by the ASO, the governing body of the Tour de France. Now, for the purposes of this video, I've deleted all data I've captured during the demos, and I'm not using any assets owned by the ASO. Okay, with that out of the way, let's move on. So in this demo, what I'd like to do is scrape the current rankings for the Tour de France. And here you see on the rankings page, it defaults to the current stage, which is stage 9. However, there's no rank available in this section at this time because the stage is still underway. So what I need to do is go back a stage, and now we're in stage 8, and it defaults to the stage rankings, but I want the overall rankings, so I need to click on the General Ranking tab. Then I need to cycle through the individual, points, climber, and youth categories to get the top 10 riders in each ranking group. Now, to get started building the application, you'll need Python and pip installed to test your code locally, as well as Selenium, the WebDriver manager, and pandas. Since the focus of this video is how to deploy a Lambda function with layers to AWS using Terraform, and not a video on how to screen scrape, I'm going to take a cursory look at the code. Please note, however, that even if the screen scraper app doesn't interest you, the process of packaging and deploying the resources in Terraform will be the same regardless of the app you're working with. So back in the code, we see I've declared a variable named URL and set it to the path of the rankings on the Tour de France site. Now, scrolling down a bit in the code, we see the main processing starts with a try block. And what I do is I print a message out to the console that I'm checking for the current stage. And this is on the rankings page. So I'll use the driver to find an element where the CSS selector is equal to no ranking LA. And if that is displayed, then that means that there are no rankings for that stage, and then I'll have to go back a stage by finding the prior stage element and then clicking on it. If while trying to find these elements they don't exist, an exception will be thrown, in which I'll jump down to the except block and then print the message on the current stage with the stage number. Next, I'll print a message to the console that I'm getting the general rankings, and then find the General Ranking tab and click on it to get to the General Rankings data. Then I'll execute code to find all the ranking tabs for the individual, points, climber, and youth rankings. And then loop through the ranking tabs, and for each rider in the current tab, I'll grab the appropriate information to set the rider's rank, number, country, name, and team in the rider's data. Then I'll append the rider data to the rider's data. Then I'll use pandas to create a data frame, passing it the rider's data, and then write it out to the JSON file, and then exiting the application. Now, as far as scraping, we have two different modes in which we can launch the browser. The first is a headless mode, which we'll want to do on Lambda, which launches the browser behind the scenes, and we don't see the scraper going through the motions of going from tab to get the data. The other mode in which we could launch it actually launches a browser on the screen, in which case we'll see the scraper going through the motions of getting the data. So for this first demo, I'll uncomment this code, which will launch the browser and then maximize the window so that the scraper has the entire window in which to grab content from. So what I'll do is go ahead and run the application. And now we see the page is launched and it's currently on stage 9. Now it's moved back to stage 8 and it's on stage rankings, and now it's gone to general rankings and it's getting the individual rankings. Now it's gone to points, now climber, and now youth. And then the browser is closed. So if we look at the output, we'll see that it started by checking for the current stage. And remember, it started on stage 9, but there was no ranking indicator displayed at this time. So then it clicked the page nav link to go back to the current stage for which we have data, and then started to get the general rankings on the general rankings tab. Then it got the individual rankings, and if we open the data folder, we see the individual JSON file, which has the data for the first 10 riders. Then it got the points rankings, the climber rankings, and the youth rankings. And if we look at the youth JSON file, here we see the rankings for the top 10 riders. And finally, it closed the browser and wrote complete. Now, for the second demo, I'm going to comment out the code to launch the browser on the desktop and uncomment the code for headless mode. Now, I'll open a terminal and rerun the app. Now, it's actually launched the browser, but it's in headless mode, so we don't see it. But we see the scraper going through the motions of checking for the current stage, going back to the previous stage, and then getting the rankings for the individual, the points, the climber, and the youth groups. Now execution is complete. Now, this worked fine on my local computer, where I'm running Python 3.8, and I have my packages installed globally. However, when we run this on Lambda, we need to slightly modify the code to work in Python 3.7, and we have to be able to install the drivers on a path that Lambda can find. So we'll be using Lambda layers. But before we move to Lambda, let's take a look at the differences between our code in the first demo, which I've renamed to demo v1, and the new file demo v2. So to start out, in demo v1, I was using pandas to create a frame to build the JSON that I was writing out to files. In the case of the Lambda version, I'm not going to be using pandas, and I'm not going to be writing files out. I'll just be building the JSON and displaying it in the console. Now, because it's running on Lambda, if you wanted to, you could take the JSON and store it as objects in S3 buckets, or take the data and put it into DynamoDB tables. But for this demo, writing out to the console is fine. And you'll notice on demo 1, I was importing the Selenium WebDriver Chrome service and the WebDriver manager for Chrome, and then using them to install the Chrome driver when I instantiated an instance of Chrome's WebDriver. In the Lambda version, I won't be using the WebDriver manager. We'll be using the packages in the layers. So I'll start by instantiating an instance of the Chrome WebDriver and then maximizing the window. And because we're going to be running this on the local machine first before moving to Lambda, we'll actually launch the browser like we did in the first demo. Then we'll move on to a headless mode for Lambda. Again, I have a URL pointing to the rankings page, and then the rest of the code to scrape the data, and then print the data to the console for each ranking group. Now let's go ahead and launch a terminal. And run the app. Now we see it's launched the browser. It's gone to stage 8. it's moved to the general rankings tab, and it's getting the individual data, the points data, the climber data, and the youth data. Now it's complete, and if we scroll through the console, we see the data for the individual rankings, the points rankings, the climber rankings, and the youth rankings. Okay, with our demo v2 version modified and running on our local machine, let's prepare to move to Lambda. And to do that, I've created a new version and called it demo.py. Here we see the imports are the same as demo v2, but whereas in demo v2 I was launching the browser on the desktop when running locally, when we move to Lambda, I'm going to run in headless mode. And I'll also need to point to the binary location for the headless-chromium executable, as well as the chromedriver. And those will be in /opt. And again, these will be layers, as will the Selenium driver. The rest of the code is the same, except that it's wrapped inside of a getRankings function, which takes an event and a context because this will be running on Lambda. So the next thing we need to do is prepare the zip files for the Lambda layers for Selenium and the chromedriver. So I'll go ahead and open the terminal, and I'll run a pip install command to install Selenium 3.8.0, which will run on Lambda, and put it inside of a python lib python 3.7 site packages folder. And I'm specifying a python 3.7 folder because we'll be running in 3.7 on Lambda. And now we see we have a Python folder with lib python 3.7 and site packages, which contains Selenium. Now I'll go ahead and zip the Python folder into a selenium.zip file. Now let's jump over to the AWS Lambda console, and here we see the only function I have is for my current dev environment, and if we go into layers, we see I currently have no layers. So let's go ahead and create a layer. I'll give it a name of Selenium, and I'll upload a zip file and select the Selenium zip file I just created. This will be for x86-64, and the runtime environment will be Python 3.7. Now I'll go ahead and create it. And now we see our Selenium layer. Now let's jump back into VS Code. And now I'll run a curl command to get the chromedriver for Linux and put it in a chromedriver.zip file, as well as run a curl command to get the headless-chromium driver for Amazon Linux and put it in a headless-chromium zip file. Now I'll go ahead and unzip the zip files, then remove them, and then zip the Chromium driver and the headless Chromium driver into a chromedriver.zip file. Now I'll remove the drivers, and then jump back over to the Lambda Layers console and create a new layer. I'll give this one the name of chromedriver. Again, we'll upload a zip file. This will be the new chromedriver zip file we just created. It'll have the same architecture and same runtime. And create. And now we see our chromedriver layer. Now let's jump back into VS Code. And I'm going to rename the demo.py file to scrape.py, and then zip the scrape.py file into a scrape.zip. Now I'll jump back over to Lambda, create a function. I'll give it a name of scrape demo. The runtime will be Python 3.7. The architecture will be x86-64, and I'll create the function. Now I'll go into configuration, edit. I'm going to change the memory to 512 and the timeout to 5 minutes. and save my changes. Now I'll go back to code, scroll down, and in runtime settings, I'll set the handler to scrape.getRankings because the name of our file is scrape and the name of our function is getRankings. Now I'll go ahead and save. Then I'll click on layers, add a layer, select custom layers, and then the Selenium layer version 1 and add it. Click layers again, add a layer, custom layers. This time I'll select the chromedriver layer, version 1, add it. And now I need to replace the default Lambda function code with my code. So I'll upload from a zip file. I'll select the scrape.zip file and save. Now I'll go ahead and save the changes and deploy them. And before I test, I'll just click the Monitor tab and then view CloudWatch logs, which we don't yet have a log group, so let's jump back to Lambda, go back to code, click Test, give the event name of scrape test and save, and I'll test the code. So with the code running, let's jump back to CloudWatch, refresh, go into the log stream, and here we see our application is processing. So it checked for the current stage. It stayed on stage 9 because at this point in time, stage 9 has actually been complete. Then it's on the general rankings and getting individual rankings. Here we see the data for the individual rider rankings. Then it got the points. Then it got the climber. And if we refresh, we see it went on to get the youth rankings, which we see here. And then execution ended. All right, so we're in a pretty good place here with our application up and running on Lambda with 2 layers. So now we can move on to Terraform. Now, before we look at the code, I do want to mention that having a foundation in Terraform will be helpful here because I'm not going to take a deep dive into all aspects of the implementation. So if you're not comfortable with Terraform concepts such as modules, locals, and outputs, I highly recommend watching the prior videos in this playlist first. Now, with that out of the way, let's jump back into VS Code and get started. To get started, I'll jump into the main TF, and we see I have 4 modules defined. A module for a Selenium layer, a module for a chromedriver layer, a Lambda IAM, which will have our Lambda's IAM role and policy, and a module for the Lambda function. Starting with the Selenium layer, we see the source points to a Selenium layer folder in the modules folder, and we're passing variables in whose values come from the locals file. Now, jumping into the modules folder, and then Selenium layer, and opening the main TF, we see 2 resources, an archive file and an AWS Lambda layer version. Now, the archive file is a resource which will create a zip file for us. And this will be the zip file that we want to upload for the Selenium layer. Now, we need to specify the source directory, which is the path to the Selenium layer source. Now, if I copy this variable and jump into the locals.tf file, we see that the path to the Selenium layer source is the Selenium folder, which if we look inside of the Selenium folder, we see the Selenium packages. Next, we have the output path, which is the variable path to Selenium later artifacts. Now, let's go back to locals, search for that, and we see that this is a path to the artifacts folder and the Selenium zip file. So when this code executes, the archive file will create the selenium.zip file and place it in the artifacts folder, which is currently empty. Next, inside of the AWS Lambda layer version resource, we specify a file name, which is the path to the Selenium layer file name. So if we copy this and go back to locals, we see that too is a path to the Selenium zip file in the artifacts folder. The layer name is the value for the Selenium layer name, which is Selenium, as we saw when we manually created the Selenium layer in the Lambda console. Then we specify values for the compatible runtimes and compatible architectures, which is Python 3.7 and x86-64. So this main TF in the Selenium layer module will again create the zip file for us and the Selenium layer. We also have an outputs file here, which will provide the Selenium layer ARN, which we'll need to pass to the Lambda module when we create it. Now let's go back to the main TF and open the chromedriver layer module. And this module is similar to the Selenium layer module, the exception being that this points to the chromedriver layer folder in the modules folder, and that the variables in the locals file specify the values for the chromedriver layer, as we see here. Next, we have the Lambda IAM module, which will create a Lambda IAM role and policy for our Lambda function. So jumping into the IAM folder in the modules folder and looking at the main TF, we see two resources, an AWS IAM role policy and an AWS IAM role. The role property of the AWS IAM role policy points to the ID of the AWS IAM role named Lambda IAM role. And the policy for the AWS IAM role policy comes from the Lambda IAM policy path variables value. So if we copy this and go back to the locals TF, we see that that value starts in the root of the project, moves into the modules folder, then IAM, and then specifies the Lambda IAM policy JSON file. And looking at that, we see this policy statement allows all resources the ability to write CloudWatch logs. And in the AWS IAM role resource, the assume policy role value points to the file in the Lambda IAM role path, which again is in the IAM modules folder and specifies the Lambda assume role policy JSON file, which allows the Lambda service to perform the STS assume role action. So after this module is instantiated, we'll have both the Lambda IAM policy and the Lambda IAM role. Now back in the main TF, if we look at the Lambda function module, we see the source is in the Lambda folder in the modules folder, and that the Lambda IAM role ARN is the Lambda IAM role ARN from the Lambda IAM module, which if we go back to the IAM module and look at the outputs, we see this is the ARN of the Lambda IAM role. Then back in the Lambda module, we specify the path to the source file, which is the scrape.py file in the source folder, which is our application source code. Then the path to the artifact, which will be the scrape.zip file in the artifacts folder. The function name is scrape, and the function handler is scrape.getRankings. Here I'm specifying the memory size and the timeout and the runtime of Python 3.7. Now, if we jump into the Lambda module folder and open the main TF, again we see two resources, an archive file, which will create the scrape.zip file and put it in the artifacts folder, and the AWS Lambda function resource. Here we're specifying the values for the file name, function name, role, and handler, as well as memory size, timeout, runtime, and layers from the variables that are passed in. And the value for the Lambda layer ARNs is a list of strings containing the ARNs for both the Selenium layer and the chromedriver layer. This source code hash creates a hash of the application source code to determine any changes when running a Terraform plan and Terraform apply. And now that we've walked through the code, we can move forward and provision the resources using Terraform. But before we deploy the resources using Terraform, I'll just jump over to the AWS console and show you that I removed the prior Lambda function and layers. Now, back in VS Code, we see I currently have no zip files in the artifacts folder, and that I have the Chrome driver and headless Chromium drivers in a Chrome driver folder, and the Selenium packages in the Selenium folder. So in the terminal, I'll go ahead and run a Terraform format, then a Terraform init. Now I'll validate, which looks good. So now I'll do a Terraform plan. And we see we have 5 resources to add. The layer for the Chrome driver, the Lambda function, the IAM role and policy, and the layer for Selenium. And if we look in the artifacts folder now, we see the zip files for the Selenium and Chromium layers, as well as for the Lambda function code itself. So now I'll go ahead and apply the plan to provision the resources on AWS. And we see our 5 resources added. So if we jump into the Lambda console, we see our 2 layers and the Lambda function itself. Here we see our code, the handler, and the 2 layers applied. And in configuration, we see our timeout and memory allocation. So let's go ahead and test the code. First we'll deploy. And go to monitor and launch the CloudWatch logs. And go ahead and configure a test event. I'll go ahead and save and run the test. Now with the test running, we could jump back into CloudWatch, refresh, go into our log stream, and here we see the app is running. Refresh again, and we see we have our individual rankings, the points, the climb rankings, and finally youth rankings. And that looks good. So that concludes this demo on provisioning a Lambda function with layers using Terraform. If you found it helpful, feel free to give it a like. And if you'd like to be notified when I add more content to the channel, please consider subscribing. Thanks for watching.